Astronomer Andrea Ghez and her Galactic Center group at UCLA have been studying the motions of thousands of stars around an invisible massive object at our galaxy's core, a supermassive black hole. Their work has yielded a plethora of observations that contradict our expectations of what should exist in its surroundings, opening many new exciting research avenues. This animation was created to showcase some of their results and put them in the larger context of our galaxy, the Milky Way. Galaxies are basic building blocks of our universe. Our own galaxy is a flattened disk of stars, gas, and dust, and we are flying through a digital model of it. We on Earth are embedded within the disk of our galaxy, about halfway to its outer edge, so astronomers have only a limited view of this grand system. The outer part of this model, the disk, was built by following the pattern of another similar galaxy that we can see well, called M83. In its innermost few hundred light years, our galaxy model incorporates molecular clouds, supernova remnants, and other structures that exist in our own galaxy, designed to resemble actual features seen in Earth-based images at infrared and radio wavelengths. As we continue inward, the number of stars continues to increase, though this visualization omits almost all of them so that we can clearly see the stars that we want to focus on up ahead. We approach the stars intensively studied by Gez's Galactic Center group in the innermost light year around the center. We'll slow down time in this visualization for a moment to get a better look at an eclipsing binary star that they discovered. As their observational methods improved over more than 2 decades of work, they were able to measure not only the positions of the stars, letting them determine their orbits, but also their temperatures and ages. What everyone expected was a great many old, cool stars. Observations showed otherwise, and invited new questions about how supermassive black holes interact with their environments. Though fewer than expected, some of those old, cool stars are present. They're shown in yellow. Another enigma: the discovery of a large population of hot stars, presumably young, shown in blue. How could young stars turn up here, in an environment thought to be hostile to formation of new stars? This dilemma has been named the paradox of youth. Another surprise: many of the hot young stars are arranged in a flat disk, all orbiting in nearly the same plane. That suggests that they had formed together, an important clue to how they formed in this region that was expected to suppress star formation. A further mystery unveiled: the G objects, shown here in red. These objects are 100 times larger than any star predicted in this environment, and may be explained by the mergers of binary stars like the one that we flew by earlier. What do all these stars orbit around? It's hardly visible here, a flickering dot, observed from Earth as a radio source called Sagittarius A star. But it's not a star. Judging from the orbits of these stars around it, it must have a great deal of mass, about 4 million times our Sun's mass. Some of the stars have orbits that bring them very close to that dim point. One of them, SO2, is our hero. It orbits every 16 years, about every 3 seconds in this animation. At closest approach, our hero star comes less than 20 light hours from it, a distance comparable to the size of our solar system. So, those 4 million solar masses must be packed into a volume hardly bigger than our solar system, but emitting very little light. That clinched the case. Sagittarius A star has to be a black hole. This increased the evidence for these exotic objects by a factor of 10 million. With an unmatched view of the inner workings of a galaxy, there remains much to learn. Continued observations of these stars are probing how gravity works, and unveiling the intimate relationship between supermassive black holes and their host galaxies. For their discovery of this supermassive black hole at the center of our galaxy, Andrea Ghez and Reinhard Genzel, whose group in Germany has been doing similar work, shared half of the 2020 Nobel Prize in Physics.